From Wilmington, Vermont. Here we go. So, welcome, ladies and gentlemen. Looking at last night's homework, page 771. We are looking at problem 23, and the instructions say determine the common ratio and find the next three terms of the geometric sequence. So, we were told that this is geometric, which is rather helpful. So, in order to find the common ratio, I can divide any two consecutive terms. So, first term divided by, second term divided by the first term. Looks like this would be negative 1 over I. That's kind of weird. Let's see if that gets me the same thing. Right, I can't leave an I in the denominator, so I'd have to simplify.
You know how I found how I found R?
Is third divided by second easier? It looks like it.
Yeah, negative I over negative 1.
Yeah.
A lot easier.
So it looks like R is just I, huh?
But if you did I squared over I, you could just cancel out.
Right.
I.
Right, so what we're saying here is, yeah, if you multiply by I over I think, on this one, to get the I out of the denominator, you'd have negative I over I times I is I squared, which is negative I over I squared is negative 1, and you'd end up getting I eventually anyway. So this is an example of which two consecutive terms you choose can save you a lot of work in finding out the common ratio. So let's see. So now we can figure out the next three terms in our pattern. So we have I, we have negative 1, we have negative I, and this is hopefully a pattern we know if we happen to know I powers.
1 I negative.
Right, so I times negative I, or I to the fourth, is going to be 1, right? I to the fifth will be I, and then negative I, and it's actually repeating these four terms infinitely. And actually, we used to have a strategy for figuring out, like, I to the 27th, where we'd figure out how many times is it divisible by 4, blah, blah, blah. Let me just check. Let me expand on this problem, all right, beyond what we had to do last night. And what if I asked, find the 27th term? And I want to approach this not from our old technique for simplifying powers of I, but let's see if the formula that we have would work. So finding a sub n in a geometric, what is that equal to? A sub I times r to the n minus 1, I believe. Little one, right? Not big one. So it's not this guy. It's this guy. Who sneezes? Thank you. So let's label what we know, gentlemen. So I know a sub 1 is I know r is I know n is 27, and I don't know a sub 27 is what I'm looking for, right? So let's just do this. A sub 27, there we go, is equal to, wait, what am I thinking? I times I to the 27 minus 1. Yeah, I guess it will quickly become, I guess I don't need those parentheses, do I? I to the 27 minus 1. Yeah, and it's going to slowly become what we were doing anyways. Yeah, actually, yeah, check this out.
That's just I to the 27.
Yeah, this is I to the first. If I add all of these exponents, that is just I to the 27, and then it becomes the other kind of problem anyway. So I just wanted to point that out, that the formula technically still works for something that we already knew how to do. And then, yeah, I would break 27 up into I to the fourth. How many times does 4 fit into 27? I believe is 6 times, with a remainder of 3. Right? 4 times 6 is 24, plus 3, 27. I to the fourth is 1. 1 to the sixth is 1. So 1 times I to the third, which is what, negative I?
Yep.
So we'd have negative I as our answer. So I just wanted to verify, right, when I learn a new formula, and if we can calculate something I already know how to calculate, sometimes it gives me confidence in that formula. Even though we proved this formula earlier, it's just kind of good to see that it agrees with something that we already knew how to do. Right, so good stuff. Other questions? Preguntas?
25 is going to be hard.
All right, good. Let's, get into the next page. This looks fancy. Let's see. Man, I still got a glare there. If I push it down, I guess. Blip, blip. Man, next 5 terms. Yeah. So let's see. The first term of a geometric sequence is, so a sub 1 is a over b squared. These a's are not the same. So, this is the first term. This is some variable or something, apparently. The common ratio, r, is b over a squared. And then it just says find the next 5 terms. So I would have...
Isn't that b squared, not b sub 2?
Yes, that's awesome. That is awesome. I like it. Good catch. Hilarious. Hilarious. So let's see. So I need to figure out 1, 2, 3, 4, 5, apparently. So this is just repeated multiplication by b over a squared. So multiplying by b over a squared, my denominator, the a, I would get an a in the denominator, and let's see.
A b.
Yeah, and a b in the denominator, and then nothing up top, huh? So 1 over ab, yeah. I wrote it kind of weird. Multiplying that by, the b's would cancel out, and I'd have a cubed in the denominator, right? Multiplying this, I would get a b up top. 1 times b is b, and a cubed times a squared is a to the 5th. Multiplying by another b up top is b squared, and then a to the 7th down bottom, and then b to the 3rd over a to the 9th. So yeah, so this one wasn't as practicing a geometric sequence as it was just multiplying repeatedly and practicing more properties of exponents and stuff, but that's all right. It didn't use any of our fancy formulas, is what I'm saying. So, but what do we got? Other questions? 29.
I mean, I feel like a lot of these have done by term into decimals, like earlier on.
Oh, boo! Boo, decimals! Boo! It's like in The Princess Bride when she has the dream about marrying Prince Humperdinck and the old lady's like, boo! Yeah, isn't that the best? That's what I think of. Boo! How great is that? A sub 1 is the square root of 5. R, I don't know yet. To find r, I'll divide any 2 consecutive terms. Root 10 divided by root 5 is actually just root 2, right?
Yes.
I believe. Since they're both in radicals, I can reduce them as a regular fraction. And sorry if my r's look like square roots. I think isn't that funny?
Wait, well, I did. I multiplied that by the root 5 over root 5. And then I got the root of 50.
Over 5. Root of 50, 25 is a perfect square that goes into it, so it'd break into the square root of 25 times root 2.
Over 5.
Root 25 becomes 5, and then it's 5 roots 2 over 5, and the 5s cancel out. So.
I just left it with root 50 over 5. I didn't get an answer.
Boo! I'm sorry. I'm just having fun now. I really hope you're not going home and being sad. I'm sorry. Sorry. Let's see. I know n is equal to 9. And I am looking for a sub 9. And my a's are going to look like 9s at some point in this problem. So let's see. According to the formula, a sub 9, oh, it's starting, is equal to root 5 times root 2 all to the 9 minus 1, I believe. Right? So that is root 5 times root 2 to the 8. So that's root 5 times, that's the same as 2 to what power? A square root is the same as what exponent?
1/2.
1/2? I guess I'll write it slowly here. I'll write an extra step. So that's the same as, let's see, using power to a power property, I'd multiply 1/2 times 8, and that's 2 to the 4th. And 2 to the 4th is 16. So 16 roots of 5 would be my answer. Yeah. So I think the things that were probably catching us last night were more of our properties of exponents, simplifying radicals, all sorts of stuff like that coming back to sneak up on us. Where you're probably pretty good at doing geometric stuff. It's just these old skills that they keep throwing at us to trick us. Also, by the way, one of the things that happened yesterday, Math 4, was I had this, and then I wrote this somewhere, and a student said, bingo, because they found my 2 different kinds of 2s in one of my problems, and so we talked about that, and I was like, oh, so if that ever happens in my video, I should have people like it, or comment in the comments of the YouTube page, and be like, at 2 minutes and 72 seconds, you wrote 2 kinds of 2s, and then I'd give them a shout out or something in the next video, because seriously, that'd be the thing to watch for. It's like the Waldo. Yeah, all right, well, yeah, okay. So 3 minutes and 12 seconds, it's the same difference. What? That works. Man, yeah, you got to keep up here. You don't know what I'm going to drop today, apparently. It's a half day. So that's good. Is there any, did we get to any S sub n formula stuff?
No.
We didn't. I might skip to do 39 maybe. Ugh, that looks ugly. Yeah. How about 37?
Sure.
Geometric means? All right, I'll do 35 first. Yeah. Actually, the fact that there's 2 different signs in a geometric suggests that my R value is going to be negative, and it's going to have an alternating sign, is what's going to happen here. So let's see. It says, write a sequence, blah, blah, blah. Let's label what we know. A sub 1 is negative 2. And let's see, if there's 2 geometric means, what term is that? That would be A sub 4 is 54. And I'm looking for the A2 and A3 is what I'm looking for. So I also know that n is equal to 4, and I'm looking for R. All right? So plug these into our formula. I will have 54 is equal to negative 2. Nope. Yep. All right. Times R to the 4 minus 1. That's kind of yellow, isn't it? Yeah. Divide by negative 2. Divide by negative 2. Orange is supposed to be my primary right now. That's what? Negative 27 equals R to the 3rd. And then I could cube root both sides. Do I have to plus or minus and not forget it?
No.
Nope, because odd roots only have one answer. All right. So then I'd get R is equal to cube root of negative 27 is actually negative 3. All right. And odd roots can also be taken of negative numbers, right? Because negative 3 to the 3rd power, right? Negative 3 times negative 3 is positive 9 times a negative 3 is negative 27, so it works out. Question?
It works. I had just done 27 to the 1/3 power. That works.
Yep. Although you'd still have to get the negative in there somehow, but yeah.
Well, it was a negative 27.
Okay, yep. So yeah, 1/3 power and a cubed root are the same thing. Did you actually answer a 1/3 on your calculator? Or?
Yeah.
Wow. I've never tried that, I guess. But yeah, I guess that would make sense if it would work. I would hope your calculator could communicate that in, yeah. Negative 2, and then I've got blank, blank, and 54. By the way, if you didn't know that this was going to be the 4th term, I recommend actually writing this out and being 2 geometric means, so 2 terms in the middle, and then it'll be more obvious, oh, that's the 4th term, right? So definitely do that. So let's multiply negative 2 times negative 3, that's positive 6. Multiply that by negative 3, that's negative 18. And just to verify, multiplying this by negative 3 is positive 54. So 6 and negative 18 are 2 geometric means between those two, blah, 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 blah. Blah, 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 blah. And let's see, and you guys got lucky and didn't have to use your second formula last night, so let's do that now. Let's see. I don't know. Do you think I'll have enough room down here? I don't think so. I'm going to scroll over. Yes, bless you indeed. And let's label what we know. So I know the first term is 5/3. I know that the...
Should I be tacking this onto my homework?
Yeah, or you could follow along. I'm fine with that. The R value, which two numbers should I divide to get my R? 15 and 5. Yeah, don't waste your time dividing by a fraction. Right? Divide the things that look easy. Right? Oh, okay. Like, isn't that a lot better? Right? So choose wisely. Or I wouldn't mark you wrong for choosing the harder path. It's fine. Let's see. The first 5 terms, so n equals 5. I want to point out that I don't know A5. But do I need it? I don't remember. No, I don't think I do for this formula. I don't. So forget you, A sub 5. And I'm looking for S sub 5. All right? Let me actually write down the formula here. Let's see if I remember it. So S sub 5, wasn't it A sub 1 minus A sub 1 to the n all over 1 minus R? Or no, was this an R? Let's see.
Yeah.
Did I get it right?
And there's an R in there.
Ah, blast. Times R to the n. There it is. Okay. 1 minus R.
Because you told us we'd get it wrong most of the time because we do n minus 1 and it's not.
Right, so I remembered that it was n and not n minus 1, but I did forget that. Yeah, that would make sense for there to be an R there. So let's figure out what is S sub 5. S sub 5 is 5/3 minus 5/3 times R is 3 to the 5 minus 1.
No.
Nope. What did I do? Oh, man. I even had it written right there. Classic. 1 minus R is 3. There we go. Okay. So don't combine those. All right? You got to PEMDAS this. You got to exponent. You got to multiply before you subtract. It's super common for people to be like, oh, 0. That's great that that worked out. Nope. Nope. 5/3 minus 5/3 times, what is 3 to the 5th? 81 times 3, is it? 243. Oh, and actually that will partially cancel with this 3 in the denominator, but I don't want it to yet, do I? No. Let's see, I know we could have just gone into decimals here. I'd probably let you get away with that at this point, but... so let's see, so this is 5/3 minus 5 times 243. It's going to be
1,200.
all over negative 2. 5 minus that is going to be what? Negative 12, 10? Nope. Yeah. All over 3. All over negative 2. Make that vinculum larger there. Is this number divisible by 3?
No,
How would you know?
because the fact that
Digits?
digits don't add to multiple 3.
Right. 1 plus 2 plus 1 plus 0 adds up to 4, which is not in and of itself divisible by 3, so I know that's not divisible by 3. How do I deal with this fraction?
Multiply by negative 1/2.
Multiply by the reciprocal of the denominator, so 1 over negative 2, or whatever you want to think about it as. So let's see, these minus signs would cancel out, and I would...
Cross to the 605.
Oh, yeah. That's right, that will cancel. 2 goes into 2 once, and then that 605. Is 605 divisible by 3?
Nope.
Also no. So 605/3. Which, for my decimal fans out there, I bet it's going to have a 3 repeating or a 6 repeating. It's 201.6 repeat. I guess with that repeat symbol, it's exactly equal, isn't it? Actually, that's one of the cool things that's going to happen with limits. Oh, I love this part. Oh, I can't wait to teach this, guys. I'm so excited. Infinite decimals, I can represent as an infinite sum of numbers. So like 0.1 repeating, I could represent as 0.1 plus 0.01 plus 0.001 plus 0.0001. and like have infinitely many of those, and then I can use limits and the sum of the geometric infinite series to prove some of these infinite decimals as fractions. It's going to be good stuff. I love it. Man, I'm so glad to be teaching this. Sorry, a little excited. So I think that's good for homework. We did this little bonus problem. I might have to look back at these homeworks and make sure that I actually get some practice on both formulas, but that's okay. I think we did fine. So thank you.